So we should move to the following speaker, which is Ernesto Contreras.
Hi. Hello. Hello,
Hi,
everyone.
Can you hear us? Okay, so Ernesto, if you could share your screen just to see if we can see everything properly.
Okay, let me see. Can you see?
Yes, I think it seems okay. Yeah, I hope there is no cutting at the edge or something. It seems that we can see everything more or less. Or maybe you can try the following slide if we can see the.
Everything is okay now?
Yes, it seems, yeah. Okay, so yeah, I guess we can start. So Ernesto will tell us about gravitational cracking and complexity in the framework of gravitational decoupling. So you may start, Ernesto, and you have
Okay, thank you.
25 minutes.
Okay, thanks. Okay, first I would like to thanks to the organizer because this talk was supposed to be last Monday, okay? But I had technical difficulties. Okay, so I would like to tell about the gravitational decoupling, gravitational cracking, sorry, in the framework of gravitational decoupling. This is the plan of the talk. I will introduce the concept of gravitational cracking, and then I will motivate gravitational decoupling and the complex factor in order to study gravitational cracking in systems constructed by gravitational decoupling. And then I will show you some of the results, okay? So gravitational cracking corresponds to the situation in which after the fluid departures from equilibrium, its radial force is directed inward in the inner part of the sphere and reverses its signs beyond some value of the radial current. It's not a novel idea. It was introduced in 1992 and now is considered as a stability condition for interior solutions. I'm defining cracking, but we have another situation in which the force is directed outward in the inner part and inward in the other part. So in this case, we talk about overturning. But for the sake of simplicity, in both cases, I will say cracking. But these are similar situations. So the idea is very simple. Suppose that you have a, can you see my draw? Yes?
You are asking if we can see what exactly?
Yes. Okay.
We can see you drawing this.
Okay, great. Okay, suppose you have a self-gravitating spheres and suppose that this system is in hydrostatic equilibrium. Okay, so this is static and spherically symmetric spheres. So we have two forces here. The first one is the gravitational pulling, which goes inward the spheres, but you need another force, an auxiliary force, which allows you to take your system in equilibrium. This force is the pressure, of course, which points outward and should be monotonously decreasing in order to ensure that this system is in equilibrium, okay? So the thing is that I would like to perturb the system, these systems, and study its response just after the system departure from equilibrium, okay? So if we want to do that, we need to consider the Thorman-Oppenheimer-Bokov equation of the system, which in a spherically symmetric and static system reads like this equation. Because when this equation is fulfilled, the system is in equilibrium, in hydrostatic equilibrium. So this part, as you know, this part corresponds to the forces related to the pressure, and this part corresponds to the gravitational part. Okay, so we have a balance here, and if we write this equation in this part, we have this a gradient of pressure, which has units of force per unit volume, and the other part corresponding to the gravitation. So if the system is in hydrostatic equilibrium, it should be 0. Okay. Okay, so I would like to perturb the system in order to ensure that the total force, this R is the total force per unit volume, of course, is different to 0 just after perturbation, okay? In order to ensure that I can use the same expression, of course. So the thing is that how can we perturb the system? So this is the total force written in terms of the structural quantities, the radial pressure, the mass, the energy density, and the anisotropy, okay? So the scheme that I would like to develop is the following. So let me assume that this force is different to 0 and the perturbation will be associated with perturbation of the free parameters of the solution. This is the same R, but sorry, but it's supposed to be the same, but modified, the modified force. Okay, so I would like to conserve the first terms in a perturbation, but important, I would like to assume that the radial pressure maintains its functional form. What does it mean? It means that I would like to perturb the system, the gravitational sector, but I would like to maintain the pressure the same. So at the end, I can ensure that this R is different to 0, okay? And we can explore if this quantity change of sign at some radius. An important point is that gravitational cracking is associated with local anisotropy. Local anisotropy plays an important role. So if we want to obtain an anisotropic solution, this is that we do in general. So we take the Einstein field equations, the metric parameterized in spherical symmetry in this way. And this is the standard energy momentum tensor for an anisotropic fluid. So we have 3 equations with 5 unknowns. So which is the plan? The plan is that we have to provide an equation of a state or a geometric constraint as Karl-Markov condition, for example, for the metric, or a condition on the anisotropy, okay? Indeed, we need combination of these conditions because, as I said before, we have 3 equations and 5 unknowns. We need to provide 2 auxiliary conditions. So the equation of state is okay, but I would like to replace these other constraints, okay, in order to avoid to give information by hand. So this is where gravitational decoupling enters. So I would like to, I know there's no time to explain in detail what is gravitational decoupling, but I would like to motivate the use of gravitational decoupling by saying that this strategy allows you to decrease the number of degrees of freedom because you ensure a particular solution, a particular sector of the Einstein equations, which is well behaved and which corresponds to a well-known solutions. So the thing is that we assume that the source of the Einstein equations can be split into a seed solution or a known solution and an other source, which is unknown. And this alpha corresponds to certain parameter, which allows me to measure how this source modify the effect of the original source. And this together, the modification of the metric in this particular way. So the radial metric should be modified in this way, and the temporal metric, sorry, and the radial metric in this manner. So today I would like to talk about gravitational decoupling through minimal geometric deformation. So minimal means that I will take G, this other function, at 0. So the temporal component will be the same, and I will modify the radial component of the metric. After doing so, we can decouple the Einstein equations in 2 sets. This set is trivial because this is known, okay? So we have an equality here, 0 equals 0. So the other sector is the so-called decoupling sector. In the other sector, we have the components of the unknown solution, of the unknown source, and the new function, which allows me to perturb or modify the radial metric. So here we have 3 equations, but 4 unknowns. The unknowns are f, theta 0, 0, theta 1, 1, theta 2, 2. Okay, so indeed, I could reduce the number of degrees of freedom from 5 to 4. Okay, so the only thing that I have to do is provide only one equation of the state to close the system, right? Of course, at the end of my computation, I need to ensure that these conditions are fulfilled, which are the Darbois conditions. Okay. So at this point is where complexity factor enters, the definition of complexity factor. Complexity factor is based on the idea that the least complex gravitational system is characterized by an homogeneous energy and isotropic pressure. This is the simplest system that we can imagine in general relativity, okay? So if you go away from this situation, we have a complex, in quotation marks, complex system. Yeah, so this is a new concept introduced a few years before. And the quantity that measure this complexity is encoded in this scalar, and this scalar is a consequence of the orthogonal splitting of Riemann tensor. So you can find the details in this work. And at the end, this scalar depends on the anisotropy of the system. In this case, pi, capital Pi corresponds to PR minus P tangential. So minus this integral, which have the derivative or the gradient of the density. Of course, this quantity encodes all this information, because when you have an homogeneous system, this derivative is 0. And if the system is isotropic, this anisotropy is 0. So we can take this a candidate to measure this complexity factor. Even more, in the context of gravitational decoupling, we can write the complexity factor as the complexity factor of the seed solution of the well-known solution, for example, Tolman 4, and the complexity factor of the new sector or the unknown sector. For more details, we can check this, this paper. Okay, okay. Now, the work, the results that I want to show you today are in this work. You can find in this work. And in this work, we base our study assuming the complexity factor as the auxiliary condition that I need in order to close the system. Recall that after gravitational decoupling, we decrease the number of degrees of freedom from 5 to 4. And now if I use this definition of complexity as an auxiliary condition, I'll close the system. I can close the system. So in this case, we assume that this is one of the results that we obtained. There are more in the paper. So we assume that the coupling sector has vanishing complexity. That means, of course, given this, that if this vanish, we are obtaining a family of solutions with the same complexity of this source. For example, if you consider that this source is Tolman 4, the new solution, the extended solution, will have the same complexity. So we have a family of solutions with the same complexity, okay? So the solutions are given by these expressions. If we set alpha equals 0, we recover the original solution. We can check that this is Tolman 4, okay? When this term is 0, this corresponds to the metric of Tolman 4, and rho 0 and PR 0 corresponds to the density and pressure for the Tolman 4 solution. Isotropy is 0, okay? And from here, we need to construct the structural functions in order to construct the total force, okay? Which in this case, we recognize the parameters beta and the other parameter chi. These are the parameters. These parameters are related, are defined in this slide. We can write all the quantities in this way. So this beta is the ratio between this constant, this parameter that appears in the original Tolman force solution divided by the radius of the solution. X corresponds to the normalized distance, and this chi corresponds to the ratio of the radius of the original Tolman force solution divided by the solution that the extended system has to, in order to the complexity be the same, okay? So as a consequence, we have this. So this is the plot of the total force as a function of X for different values of gamma. Who is gamma? No, sorry, for different values of chi. Okay, remember chi corresponds to this ratio here. So if chi increase means that the ratio of the radius of the new solution, of the extended solution, is less than the radius of the original Tolman force solution. So it's a tiny star. So this is 0.1 for 0.3, 0.5, and we have this situation. Note that we have a kind of transition between the situation in which we have cracking, in this case overturning to be more precise, and then the surface in which cracking occurs displays to the right, and then we have a situation in which cracking doesn't exist. So in this situation, we can say that the system is stable, okay? So we have another plot. In this case, we vary gamma. Gamma is defined as the parameter which allows us to connect the variation of beta and the variation of chi. So in this case, occur the same. So the surface where cracking occurs displays to the right, and then we have a situation in which the system becomes stable. So this is another situation, the opposite situation, in which we have a decreasing values in beta. If beta decrease, means that the radius increase, but this radius is related to the compactness of the source. So this is the Darmo condition applied to the solution. And here we can identify the compactness parameter. So here we have 1 divided U, where U is M divided R, the compactness parameter of the source, minus 3. Okay, so this is related with the compactness of the source. So now we have that the cracking occurs in deeper regions of the stars. And in this case, we were not able to find a situation in which the system is stable. Okay, okay. So these are the few results. For more information, you can check the paper or ask me some question if you want. So some final remarks are that gravitational cracking has been used as a criterion of stability of self-gravitating spheres and is used today with the same. And it important, this part, the behavior of the total force doesn't ensure that the system will evolve in this manner. So to this end, we need to solve the total dynamical equations. So it allows us to have an idea of what could occur with the star after perturbation. That's it. Okay. So it can be thought, must be thought as a snapshot of the situation just after perturbation. Okay. So thank you for your attention. If you have any question.
Yes, thank you very much. Now we have time for questions, remarks. Yes, so we can start with Professor Abramovich.
Perturbations with general relativity are tricky subject. And one of the reasons for this is that we have coordinate freedom.
Okay.
So sometimes when we perturb, it is not that physics is perturbed, but coordinates are changed. And I know how we are dealing with this problem in cosmology. in cosmology, there is an approach suggested by Jim Bardeen and then developed by himself, Marco Bruni, and other practitioners of general relativity. So I would like to know whether there are similarities in your approach to the approach of Jim Bardeen concerning perturbations in general relativity. The thing is that the scheme which Bardeen and collaborator proposed is based on general covariance. So it is obvious in his approach that the perturbations are not trivial things connected with changing in some way coordinates, but they are physical. So there are constraints that the things which should be perturbed are zero in the background, like for example, shear, etc., etc. So my first question is, how close your approach is to this covariant approach of Jim Bardeen and collaborators? And the second question is trivial. Is your perturbed space, does your perturbed space-time has the same Killing symmetries as unperturbed space-time? Do you preserve Killing symmetries? Thank you.
Okay, sorry, but I have some problem with the audio. I think that the echo is very high. I'm not sure if I understood the questions. Probably.
Jim Bardeen in cosmology, perturbations. How close are you to this scheme?
It's not related with this. So we are assuming, for example, that anisotropy.
I know that it is not related to that, but it was done using some principle of how to do perturbations in general relativity. I'm not talking about his specific way, but of the principles that you cannot do perturbations in general relativity saying, I have the background, so let me have a tensor multiplied by a small quantity and linearize or so equation. There are constraints, gauges, and things. So I'm asking about this. I know that it's not the same as Bardeen, but in principle.
Okay. No, we're assuming here that the sources of perturbation are anisotropies, indeed. For example, related to intense magnetic fields inside, or viscosity, which are the you know. But if we have a change in this quantity, we can talk about a perturbation in the system itself. Okay. This is the physical explanation of what we are meaning by perturbation of the system here.
Yeah, I thank you for the answer, and I think there was one more question by David Alvarez. If you can make it louder. So
Hi, thank you very much for the talk. My question is very simple. How dependent are your results on the equation of the state that you have chosen? Because you have analytical solution for the theory, but in reality, you may consider whatever equation of state that you
this is a very interesting question. For example, in this case, we obtain analytical solutions, but for example, when you suppose that the equation of a state is like a polytropa, this is a polytropic equation of a state, it is impossible to obtain an analytical solution. So first, we need to solve the system numerically, and then we have to use this information in order to construct the total force to study the perturbation there, okay? But it depends on what kind of equation of a state you use. So in this case, in the framework of gravitational decoupling, we are assuming this complexity factor, but we could assume a barotropic equation of a state in the decoupling sector. And in this case, it's also easy to obtain analytical solutions. But in general, it is not possible to obtain analytical solutions. But it is possible to study, to apply this scheme in this situation. It is possible, but numerically.
Okay, thank you, Ernesto. And I think we have one more question among online participants. So, Sudipta, if you could ask.
Yeah. Hello. Yeah.
Hello.
Can you hear me? Yeah.
Yes.
Yeah. So my question is like that. As you said in conclusion, that it is just a snapshot. So in order to infer anything about the fate of the stability, I mean fate of the star, and to study the stability, we have to see the system dynamically. I mean through some numerical simulation or something like that. So how complicated is it to use this approach? I mean, wouldn't it be too expensive in the sense of, I mean, time and also power?
It's possible. It is possible. I don't know if we can connect directly the consequences of this cracking, okay, this is snapshot, and then connect with the dynamical part. I think that it could be possible, but the dynamical of this system have been studied in some regimes. So I think that it is not very difficult to adapt the discussion to the situation. Okay.
Thank you.
Okay, right.
Okay, so if there are no urgent questions or comments, I guess we can thank Ernesto again for a very nice talk.
Thank you.
And we will move on with the coffee break. So I guess we are pretty much on time. So we have approximately half an hour, and the next talk starts at 15:35. So 5 minutes.